All right, we're going to continue with part B. Now, part B is a little different from A. If you remember, part A was finding the average rate of change over a certain span. This part we're looking at the instantaneous rate of change. So, for example, it says any moving object. So, suppose you're in a car and you're driving at 100 kilometers per hour. And you went to, I don't know, a distance, you went to Niagara Falls or something. You know that your rate of change or speed will change over time, right? At sometimes you might be going 120, sometimes you might be going 80, depending on traffic. But your average rate of change just takes how long it took you to get there and the distance. Now, instantaneous rate of change is a little bit different. It's going to say, well, how fast were you going at a certain period of time? So maybe after 30 minutes, how fast are you going right at that one instant? And that's what instantaneous rate of change is. So if you imagine on the graph, in this case it says a ball bearing was dropped from a tall building and the distance has fallen after 2 seconds is recorded. So after 0 seconds, the distance has fallen to 0. After 2 seconds, the distance that's fallen is 20 meters. And after 4 seconds, the distance that's fallen is 80. So you can see that it's speeding up. It's getting faster as the ball bearing is falling from the top of the building. So what we did in the last section, we said, well, if I want to know the average rate of change between 2 and 4, we just found the slope of a line between 2 and 4 like so. Now what we're going to do is we're going to be dealing with not between 2 and 4, but right at 2, for example, if I wanted to know how fast the ball bearing was falling right at 2 here. Well, the idea is its slope is always changing. Let me get a different color here. But I want to know this slope here. One that just touches that line, doesn't cross over it, but just touches it. That would be the slope of the line. But the problem is we only have one dot on that line. We only have that point at 2 and 20. We don't have a second point, so I wouldn't be able to use the slope formula to find out this. Now that red line is called the tangent line, and we're going to be looking at that. We're going to be trying to find out the slope of the tangent line. That's a line that just touches the curve, but doesn't actually pass over it. So see an example of one down below here. Here's another example of a tangent line. It just touches P but never crosses over. This is what we're looking for the instantaneous rate of change. Remember, average rate of change had 2 points on the line, and we found out the slope between those 2 points because we had coordinates for them both. But for instantaneous rate of change, we only have one spot because I'm only interested in that one spot in time, how fast something was traveling or the rate of change right at that one time. So I don't have points on this tangent line here or here in order to help me. So what do? From the investigation, you should discover that the instantaneous rate of change of a variable at a particular instant, right at P there, is given by the gradient, which we said was slope of the tangent to that graph. So the slope of that red line. For example, the graph alongside shows how a cyclist accelerates away from an intersection. So his distance is increasing over time. Right? Distance is increasing as time increases. So the average of the first 8 seconds is shown over there on the left, 100 meters divided by 8. We know that. That's from here to here. The slope of that line would be 100 divided by 8, which is 12.5, which we have over there on the left. Notice the cyclist's early speed is quite small, right? They're not traveling very fast in this section, but increases as time goes up. So the slope gets more and more steep over time. So that line gets more and more steep over time. To find the instantaneous rate of change at any spot, for example, where t is equal to 4, right here, we draw the tangent line. So I want to know what is the slope of that line there, because that would be the speed, the rate of change right at 4. The tangent line passes through 2 spots, so we have an endpoint here and an endpoint here, and we can use the slope of those 2 endpoints once we've drawn that tangent line to find the slope. So as we said, we have 7 and 40, and over here we have 2 and 0, and we can use the slope. That's where we get the 40 take away 0, 7 take away 2, work our way through, and we find out that right at that spot we're traveling at 8 meters per second. So that's the first way that we can find out the slope of the tangent line if we have a grid, and that's what we're going to look at, the ones down here. For each of the following graph, estimate the rate of change at the point shown by the arrows. So when t is equal to 1, so you'd have to draw a tangent line to it. Or B, you'd have to draw a tangent line. Something like that. And that one doesn't really touch it, but it should touch it. It should be a little bit closer. Next one here. Whoops. And that one there. So if we're trying to find out the slope of these ones, we just need to choose some points that are on the tangent line as best as we can. So the line's not necessarily completely straight, but if I just try to find some spots along that tangent line, maybe I pick one here, and I don't know, maybe the spot over here, and I find the slope between those. So we would have 0 and 1 for the first one, and over here we'd have 2 and 3, and we'd find the slope of those. Same goes for B over here. Drew my tangent line maybe here, and I would find the slope of those. So we'd have like 2 and 1, and up here we would have 4 and 7. Right, so we're just getting points along the line, and we use our slope to calculate it. So for A over here on the left, 3 take away 1 and 2 take away 0. We would end up with a rate of change of 1 in this case. So right at t is equal to 1, we should have a rate of change or a speed of 1 meter per second. Same goes over here. When I'm finding my slope, would be 7 take away 1 all over 4 take away 2. Now in this case we would get 3. So that means 3 kilometers per hour in this case, right? Because we're using the different unit in this case. So same for the ones that are down below. We just find points that are on the line. As we continue, water is leaking from a tank. The volume of water left in the tank over time is given in the graph alongside, so over here on the right. How much water was in the tank originally? Well, if I look here, I see that it had 8 liters of water in the tank originally. That's at time 0. How much water was in the tank after 1 hour? So we'll look here, and I'd say it looks like there was 3 liters in the tank after 1 hour. How quickly was the tank losing water initially? So what does that mean? That means right at the beginning. How fast was the water decreasing? So if we're looking at the spot at the beginning, so I'm trying to take these ones off here, and I wanted to draw kind of a tangent line of as best to represent what's happening originally. I'm going to find 2 spots that would be on that tangent line, so perhaps these 2 here, where we would have 0 and 8. And 0.5 and 4, and I find the slope between those ones. So subtracting my y's, we'd have 4 take away 8. Subtract my x's, 0.5 take away 0. We would end up with -8 or -4 over 0.5, which is -8 liters per hour. That's right off the bat. We know that it slows down later on because if I get a different color here, we can see that it slows down here, a little flatter all along. So that's the fastest originally. It started out at that speed based on our tangent line, but then it slowed down. So let's look at part D. Part D says, how quickly was the tank losing water after 1 hour? So I'm going to find out the tangent line at 1 hour. Take off these. So at 1 hour I see the dots right here. So if I was to draw a tangent line, a line that would just touch it, maybe something like that. I want to find out the speed. So I can choose 2 spots. So I don't know, maybe the beginning over here, which is at 0 and 5.5 maybe. And then maybe this spot over here, which looks to be at about 2.5 and 0. And I'll find the slope between those. I would subtract my y's. 0 take away 5.5. Then subtract my x's. 2.5 take away 0. We get negative 5.5 over 2.5. And when I divide those ones together, it's going to give me the speed that the water was leaving the tank. Negative 5.5 divided by 2.5, which is negative 2.2 liters per hour. So remember, it's always changing over time, but we just happen to come up with how fast it's going right at that one spot. We created a tangent line.